provide this.
Okay, hello, good morning, everyone. I just want to make sure people can hear me and they see my screen. I'm Jim Marino. I'm one of the people involved with the Eclipse Dataspace Connector. And as Marcus said, I'm going to cover the architecture and architectural principles around the connector. And I hope once we go through the talk, at the end of the talk, everyone will have a pretty clear picture of at least at a high level, how the EDC is architected and some of the principles and thought that went into designing the code base. Okay, so the way I'd like to do that is really discuss the architecture by highlighting really four key technology challenges of data sharing. And many of you have probably already encountered these challenges and probably asked yourselves these questions. So the first one is really, how do I find data? How do I discover it? How do I see basically in a data space what's out there that can be shared? Similarly, one of the questions you'd probably ask is, how do I publish my data in a secure way? So how do I make it available for others, but at the same time, how do I do that securely? And then the third question relating to that is really, how do I share my data in a multi-cloud environment or in a diverse technology environment? So within a data space, different participants may be running on different infrastructures. So how do you enable that when there is really no centralized infrastructure? And then the key question really that Boris touched on before this talk was, how do I maintain control over my data once it's been shared? So how do I guarantee that the usage requirements and obligations I'm placing on that data are followed once my data has been shared with others? So those are the four kind of key questions I'd like to address as we go through the architecture of the EDC. Okay, so just as an introduction, as well as just so everyone has a level set, the Eclipse Dataspace Connector EDC, it's 100% open source platform, obviously designed to address the problems of data sharing. And really, the key thing, the way I'd like to describe the project is it provides the technology you need to create and participate in a secure data space. As you can see there, it's really a global effort. These are some of the partners that are involved in actually working on the project directly. So I think the key thing there is it really represents a wide geographic region. Okay. So in terms of an agenda, the first thing I'm going to cover is what role does the EDC play in a data space? Then I'll move on and talk about some of the architectural principles and design. So give you a little bit of the history and thought behind the design of the EDC. Then I'm going to talk a little bit about the core foundation, the technology platform that underpins the EDC, and we'll go into a little bit of what the connector is and how that works. And I'm also going to spend some time on policy enforcement. And hopefully we won't run out of time. I'd also like to talk about the federated catalog services and some of those components that we also provide within the project. So, as Naut said, one of the things I like to highlight about a data space is really four key technology pillars. And you can see them down there: identity, trust, policy, and interop. So what that really means is, in terms of identity, each participant needs to remain in control of their identity. Likewise, with trust, each participant in a data space needs to decide for themselves who they're going to trust with their data. And then in terms of policy, basically each participant also has to maintain control over their data in terms of deciding under what policies their data is to be shared. Okay, so again, they maintain autonomy over the obligations associated with their data. And then I think the fourth thing, and Boris touched on this on his talk, in terms of there's no centralized, essentially no centralized repository or centralized infrastructure in a data space. The key thing there is each participant has to remain in control of their own infrastructure. So what that entails is interop. In a data space, you can't mandate a homogeneous infrastructure. You have to allow the participants to maintain control over that themselves. And you can see there the EDC really brings all of those, essentially those four pillars together. And what it allows you to do within a data space is essentially discover other participants and other data that's available in the data space. It allows you to publish your data to a data space so it can be shared with others. And the third thing is it allows you to share data. So how do you connect into the data space and move data around and share it? And then the fourth, important thing is once the data has been shared, how do you maintain control over that? What are the mechanisms that are in place that allow you to do that in an automated way? Okay. So diving in a little bit in terms of the architectural principles at the core, and I like to view these things as kind of building on top of one another. The really core foundation is a modular design. So the EDC itself is written in Java, but the important thing here is all the functionality is contributed as a module. So there's the EDC is essentially built as a series of modules. You can think of it in terms of Legos, right? They're composed together. What that allows us to deliver is really a lightweight composable runtime. So different modules, you can pick and choose which ones you want to build your EDC runtime. And the key thing here, as well as in terms of a project goal, is really a focus on minimal dependencies. So the actual core itself has extremely minimal, requires very minimal third-party libraries, and the idea is to keep it lightweight as well as flexible in terms of being able to deploy in diverse environments and as well as being able to handle diverse use cases. So what we really, the core kind of base part is a very modular foundation. Okay. Related to that, the way we've designed it is all features are, there's basically extension points for all features in the system. So it's, kind of in conjunction with modularity is the capability of extensibility. So basically having all features defined as clear extension points allows you to swap different implementations. So for example, there's certain requirements around being able to do data storage. But within the system, you might need to record certain metrics or runtime operation. If you're storing that in a data store, you'd want to be able to swap that so that you can take advantage of different databases. So for instance, one use case might require on-premise deployment of the EDC. So in that case, you might want to use a database like Postgres. Another option might be you want to deploy it to the cloud. So in that case, you might want to use a cloud database service. Similarly, in terms of data storage, there's also plug points for security and for other areas in the system that I'll go through. The other benefit that this provides you is essentially allows you to create your own features and capabilities in the system as well. So you're able to plug in if you have an idea or a feature that you want. There's a way to have that plugged in and surfaced through the core EDC platform. And I'll explain as I go through in more detail how the EDC works. We'll explain that in a little bit more detail. But again, the important thing is there's a modular base. On top of that, we have an extensible design. Okay. Then the third thing is really around adaptability. So what we want to be able to do, I mentioned previously, is to be able to deploy the EDC in very diverse environments. So obviously there's cloud deployments. We want to be able to support on-premise deployments as well as edge deployments. So what this really entails then is you really need to be able to deploy the EDC with diverse different capabilities. So for instance, like I said, on the edge, you're going to need a much more lightweight, minimalist runtime than perhaps you'd need in a cloud or on-premise deployment. So you can see how these are building up. Modularity, extensibility allow us to do that because we can adapt the runtime to whatever use case we're trying to fulfill. And again, the important thing too we like to say is everyone talks in terms of scalability being scaling up or scaling horizontally. But we also think it's important that the design scales down so that you can create minimal runtimes for instance edge devices. So there's really two aspects to that capability. And again, the key thing here we like to stress is having the runtime, building a runtime that's adaptable. Okay, and kind of the final block I like to highlight is resiliency, or the fact that we're building a runtime that's highly resilient. So in order to do this, we want to have the runtime be able to leverage high availability infrastructure that you've already invested in. So a lot of our thinking, you'll see this reflected in other areas of the code bases. We want to be able to allow people to leverage their IT investments that they've already made. We don't, in other words, we don't want to reinvent the wheel. So in terms of resiliency, we want to be able to leverage cloud services like databases that support geographic failover and redundancy. We want to be able to support clustering and clustered management infrastructure. We also, the other important thing that I'll also spend quite a bit of time on in a minute is we want to be able to support and leverage existing data transfer technologies. So there's plenty of technologies out there that help with data movement and data transfer across different environments. Our goal with the EDC is really to design it in such a way that we can leverage those. Again, we don't want people to have to throw out the investments they've already made. Okay, so again, those are the kind of the four key architectural principles we have: modularity, extensibility, adaptability, and resiliency. Okay, so this slide here is basically the entire EDC architecture. So if you don't remember anything else from the presentation, just remember this slide. And as you can see there, it's actually quite simple. But I'll walk. What I'm going to do is walk through and tease out the nuances of this in the rest of the presentation. But essentially, there you can see, as I had mentioned, in terms of modularity, the core architecture, the fundamental part of the EDC is really a module system. So it's a way of assembling different modules that provide features in the system. So you can see there, there's a clearly defined SPI or service provider layer. Those are where we define the extension points in the EDC. And you can see there all the features are contributed as extensions that provide essentially services inside the runtime. And you can see in order to create different runtimes, you simply just specify the extensions you want, you load them into the system. Again, that allows for choice because you can swap in and swap out. Okay, so that essentially is the design, and there's different layers and nuances to this, but what we try to do is create a very, very simple architecture. So in terms of how this all works in practice, you can see there that what we have is a set of common modules. So we'll have common capabilities around things like identity or storage, and those are repurposed into different parts of the EDC. So for instance, we have a component for a registry, which is basically being able to register and discover other participants in the data. In a data space. And you can see there we can create a registry runtime for that by basically just loading up the core module system and then loading specific extension points that enable that functionality. Similarly with catalog services, so being able to publish and search within a data space, similar thing, we have a core module system and then extensions that allow you to do that. And then in terms of data sharing in the connector, again, this exact same approach. Core module system, we load in common modules and then specific modules for the connector itself. Okay, you can see there as we move along other services that we want to build in the future that become necessary, we can essentially do the same thing. Okay, so now I'm going to talk first a little bit about the connector, and which is really dealing with the data sharing. So I'm going back to the pillars of a data space. We're going to start with the data sharing part. I'll talk a little bit later about how do we actually publish data, but right now we'll just assume that the data has already been published into a data space, and now essentially what I want to do is share it and interact with others. Okay. So the key kind of design principle of the actual connector itself is, and this is kind of the fundamental or core to the entire system, is a separation between what we call the control plane and the data plane. So the connector itself is really divided into two logical systems. Okay, and you can see that represented in the slide here. The control plane is really about verification. So, for instance, does a client that's requesting data, do they have access? Should they have access to this data? Do they meet the data usage requirements, for instance, of that asset that they want to transfer? Are they, for instance, if you have requirements around, are they operating in a secure environment? That type of verification mechanism is done in the control plane. The other thing that it handles is contract negotiation. So when you perform a data transfer, there's an electronic contract that's established between the two participants. That electronic contract would spell out, for instance, the data usage policy. And I'll go into this a little bit more detail, how these mechanisms work. But at a high level, at this point, just keep in mind, it's the control plane that's managing this. Similarly, the overseeing, what I call the overseeing of policy enforcement, is handled by this control plane. Again, like I said, we'll go into the details of this in a minute. And the other key piece or aspect of the control plane is managing provisioning. So by provisioning, I mean any type of setup or processing you might need to do to initiate a data transfer. So for instance, if a participant wants to share, say, large data, some kind of big data for machine learning, there might need to be some pre-processing that happens over the data. Say it needs to be anonymized or transformed into a certain format. The control plane would be responsible for initiating that type of processing and controlling that. Okay. In terms of the data plane, what the data plane, in contrast, is responsible for is the actual movement of bits on the wire. So, once the verification's been done, there's a contract negotiated. You can ensure policy enforcement's going to happen, and everything's been provisioned and it's ready to go. The infrastructure that actually moves the bits from one place to another is handled by the data plane. And the key point here is that type of data transfer, there's widely varying use cases. So as I mentioned before, it could be big data. You could have streaming data, or you could have events or some other type of data transfer. But the key thing here is the data plane has to really be able to accommodate all of those use cases. Okay. So the big question is, why did we do it? Why did we do this? Why did we design it with a separate control plane and a separate data plane? And there's a number of reasons why. So the first one is we wanted to leverage existing infrastructure. So again, as I said at the outset, we don't want to, first of all, reinvent the wheel. And the second thing is we want to allow people to leverage existing technologies that they're using. So as you can see here, the actual data plane itself can be implemented or use technology such as Kafka. It could use eventing systems. It could use object storage like S3. It could use other types of messaging providers like NATs or cloud events. The important point here is that there's essentially an integration mechanism between the EDC control plane and whatever is actually running or performing the actual data transfer. So essentially what that allows us to do then is handle many different use cases. So for instance, we didn't want to reinvent and come up with data transfer protocols. Kafka handles that, or NATs handle that very well. Same thing with big data. We didn't want to create infrastructure that would require, that we'd have to be able to handle, large data transfers like gigabyte data. Things like S3 or other object storage systems are built for that and have the infrastructure to do that. So our key goal in this is really integrate with these technologies. Okay. The second reason why we did this is the reason of high availability. So one thing is we didn't want to require that all of the data transfer flow through the control plane itself, because that would mean then that the control plane has to be extremely high available and highly scalable in a way that if we can separate those, that makes things a lot easier. So for instance, by having those two distinct subsystems, if, for instance, the control plane goes out on one side, you're going to the data transfer is still going to continue. And that's actually really important, particularly in the streaming use case, because you can think of streams as just ongoing data feeds, right, that are happening all the time. So, if the control plane doesn't have to be within that, kind of interposed within that transfer, it makes things a lot easier. It doesn't necessarily have to be up, 99.99% of the time. It just makes problems much more tractable. And then the other third reason why we did this is essentially one size doesn't fit all. So like I had mentioned, there's many different types of data transfer, big data, streaming, events. And the way we have it is actually the data plane might be backed by multiple different technologies. So for instance, if you're handling big data, the connector could decide to basically use object storage as transfer. Or if you're using streaming, again, it might use NATS or Kafka. Or if you have smaller events, it might use a cloud eventing system. So the idea is that really the design that we have allows you to pick and choose based on the use cases that you have. So another kind of part of the connector that we're actually working on in this milestone release is what we're calling the data plane framework. And the idea here is it allow you to do dynamic routing, basically for data transfer. So for instance, if you want to be able to go, say on the provider side, you have data stored in S3 and you want to take it out and send it over to a participant that has an HTTP endpoint, the data plane framework is going to allow you to do that, or it'll handle that kind of routing. And again, like everything else, it's built on the same EDC foundation. So in addition to, just if you had the data transfer part built, say, purely on Kafka or purely on some other type of technology, you can also you'll be able to use the data plane framework to do essentially routing between different endpoint types. Okay. Now, in terms of the connector, I'll go down kind of the next level of detail. And the key thing around the connector itself is it's an asynchronous system. So asynchrony is really critical to the architecture of the system. And essentially the way this works is there's a client and a provider, and when a data request is made, so the client requests data from the provider, the requests are going to be represented on both sides, and they're going to asynchronously essentially transition through a set of states. So you can see here on the left here, the client will go through it in an initiated state. Then again, it'll send the request up to the provider and they'll initiate it on their end. Then you'll see it'll go through a series. They'll be provisioned, in progress, and completed. And the idea here is each of these states it's transitioning asynchronously. It's going through a series of steps on both sides. Okay, and that's a little bit different, I think, than previous architectures where you could think of data sharing as a much more synchronous operation. So, in other words, I make a request for data, and I'm going to get the data back immediately as a response to the initial request. This is a little bit different. Essentially, make a request, you'll be notified back asynchronously. Okay, it's proceeded to this step, then this step, then this step. So it's a bit of a different design. Okay, and so again, why did we do this? Well, asynchrony has a number of virtues. I like to call them. So the first thing is it allows for potentially lengthy data preparation. So if a request is made, the provider might have to go through data prep on its end. And that might involve even things like infrastructure provisioning. So it might have to provision some type of storage that the client can then go to retrieve the data. It might have to provision a stream or do something else. For instance, it might have to make some type of policy provisioning. So an example of that would be on the client. If say, for instance, if the requirements for the data were that it had to be stored in Europe, it might have to provision some kind of storage in a European data center. Again, I mentioned before, you might have data pre-processing. The key thing here is that those type of requirements could take an indefinitely long period of time. You obviously can't do that within a single synchronous request. So having this asynchronous design lets us account for that. The other thing is it allows us to achieve reliability. So essentially, as you go through each step, if one of the systems crashes, once it comes back up, it can just pick up where it started. So we do this through a series of being asynchronous and then idempotency. So basically, like any type of messaging system, the architecture, the ideas are fundamentally similar to that. The other thing it provides is high availability. So you can think of each connector when it's doing this processing is operating is a series of clustered workers. So when you would deploy a connector, say you could deploy it in a Kubernetes cluster, you could have multiple replicas of the connector working, and they're all working in unison in an asynchronous fashion. The other thing it provides is natural throttling of transfer requests. So if you're getting you get a lot of requests in, those they're received, they're persisted, and then they're operated on asynchronously. So that allows you, if you're getting a lot of requests to come in all at once, it gives a nice natural throttling because you have these clustered workers essentially picking up the work requests and processing them individually. It also allows, this is important, fairness. So in the processing of requests. So essentially what you want in this type of system is you don't want one transfer process to basically backlog the entire system. So you can think of that as, maybe you have a bunch of requests that come in and there's one for gigabytes of data. If that one coming in for gigabytes of data, it comes in, you don't want that blocking all of the other requests from completion. So what we do is by having these different states, we can essentially guarantee the way that connector works is it can say, okay, process a batch from this state and this state and this state. So we're able to basically, in kind of any cycle through the system, select a sampling from each state to progress along that process. Okay. So one question that typically comes up is, how does this impact transfer performance? So doesn't all this asynchronous, ticking over, progressing different transfer processes to the next state, doesn't that take a long time and doesn't that affect performance? So again, the thing I'd like to point out here is that you have to remember the data plane is really separate from the control plane. So we can see how this, essentially would work with streams. So, in this case, the use case, I want to be able to essentially share say a high volume data stream. It could be IoT data. The way that would work again is the control plane. The async is really handled as part of the setup and initiation of that. So once that's done, the actual data transfer, the streaming is going to proceed without any of that overhead. So that could basically drop down into an IoT streaming infrastructure. And that overhead of setup is just done during the setup phase, but the actual sending of the data is independent from that. So the answer is it really doesn't impact most transfer performances. It's just once you're done the initial setup, the actual data transfer itself proceeds without that overhead. So what I'd like to do first is talk a little bit about policy enforcement, and then we'll move more on to how data is actually published in the system. I wanted to do this because I know there were a lot of people before the talk mentioned that there was a lot of questions on how policy is actually enabled and enforced. So again, this is really to do with, how do you maintain control over your data once it's been shared? So, examples of policy is, one aspect is an example would be, these assets that I have should only be shared with my partners. So there's essentially a kind of exclusivity you want to enforce. I only want these particular partners to see these assets because they're not public. Well, maybe I have other assets or other data that is public, that anyone can see. Another type of policy enforcement, for example, would be kind of a geospatial enforcement. So my data, once I share it, I want it to remain, for example, in Europe. Okay, so to start with, there's really two aspects of policy control. Essentially, first is the role of policies when you're publishing data. So like I said, I only want certain participants or certain people, other organizations to have access or be able to even see my data. And then the second aspect is really runtime policy enforcement. So once I share data, how do I know the obligations I have around usage are being met or being enforced? Okay, so let's start with assets and policies, and this will get into a little bit of discussion in the EDC how these things are represented. So all data in the EDC is represented as an asset. So for instance, an asset could be as simple as a specific file that you want to share. An asset could be a group of big data that's stored in many different files. Or an asset could be a stream. So it could be a stream of data, which is a little bit different because it's kind of an ongoing, continually updating set of data. An asset could also, and we've had interesting use cases around this, could also be access, for instance, to an API. So the API itself could be a data API itself could be an asset. But the important thing here is in the system there's a representation of an asset, which is how data is modeled. Now, relating to that, all assets are associated with policies. So a policy might be a rule, obligation, or duty, about a particular set of data. Okay, so the key thing then is we have assets here and we have policies, and there's an association between them. So the key thing here is if we had this if we had to define policies for each asset, that would be pretty laborious, right? So we don't in the EDC. It's not that you would, for instance, you take an asset and then on the asset you define, okay, this asset has these policies, and then I duplicate that for every asset. Obviously, that would be extremely tedious and error prone. It could also be a security risk. So thinking of it from an organizational viewpoint, what you generally don't want to have happen is that every time the assets is published in the system, you specify the policy because you could forget to do it, maybe use the wrong type of policy, or you want to define basically a set of policies that apply corporate wide. So again, there's a security risk associated with that. As I mentioned too, it's also difficult, for example, for a data officer, someone who's going to oversee all of the corporate policies, really to be able to set corporate standards around that. So one of the use cases we have is companies generally have a set of standards, a set of predefined policies that they want to use across all of their data, and we want to be able to enable that. Okay, and then again, there's also the level of complexity because some assets actually might have different policies. So for instance, maybe an asset for your partners, a certain class of partners have a specific set of policies associated with them, but a different set of partners that you have, they might have completely different policies. Or you could even offer the same asset under two different usage contracts or policies. So we want to be able to support those. And if you had to do that for each policy, obviously that would get extremely complicated. So the way we handle these is through the notion of a contract definition in the system. Okay. And a contract definition is essentially a top-down design where policies are defined and they're attached to assets. So it's really you define these contract definitions, and then they're essentially attached or associated with particular assets in the system. So what we've done here in terms of the design is decouple policy authoring from particular assets. So you can define general policies that then get applied to particular assets as they come into the system. And again, obviously this provides a lot of flexibility, but it can also be simplified when needed. So for instance, you could have a user interface that lets someone, if you wanted to, take an asset and then just have a drop-down list of policies and associated with it, or potentially create a policy on the fly and then associated with that asset. So there's ways of simplifying it. The important thing is underneath the architecture itself decouples those two. Now, the contract itself contains three things, contract definition. One is the access control policy, and that's essentially private, basically control. So it's things like, this asset I only want certain types of partners to see, or this asset I want only people in Europe or in the US or wherever in Asia to be able to view and access. That type of access control you don't want to advertise, right? Because it's related to kind of your private security layout and how you have things structured. So that's access control is one type of policy that you define with the contract definition. The second thing you define is what we call the contractor usage policy, or just usage policy, and that's actually what's advertised and what you want the clients that are requesting the data to be able to see and fulfill. So for instance, this data must stay in Europe, that you would define as contract usage policy. And then the third thing is what we call an asset selector. And it's basically, you can think of it as almost like a database query. It's an expression that you would apply to say, okay, this contract applies to these types of assets. So for instance, you could say, this is a contract for my parts data, or this is a contract for my emissions data. And there would be a way then within the asset, an asset would say, well, I'm admissions data. And the selector, much like a database query, would be able to select those assets or become attached to those assets. The other kind of advantage of this whole system is you can define the policies up front. And as assets come in, policies are automatically attached to them. So you can think of it like a use case maybe from financial services. You might have a contract definition for market data, closing data for each day, a data dump that comes in and is added to the system when markets close. The contract is defined ahead of time, but as each day when an asset's published in the system, containing market data, it's basically the contract definition is automatically going to pick that asset up. So it gives you a lot of flexibility like that, or similar with machine learning. If you're having updated machine learning, you can just publish that in, and that the security policy, the access control, and contract usage policy is always going to be applied to it. Okay, so in terms of publishing data, I'll just walk through a use case how this would actually work in practice. So we have the notion of this data officer, and the data officer, they're responsible for defining contracts in a corporation and the EDC system. So again, they say, these are the kind of corporate contracts data. This is how we want to share data in this data space. Here are the contracts. The data officer would in general define those. There could be a UI where they enter those in, and then they get loaded into the EDC system. Okay, that's separate than the data owner, and the data owner might be at a different level. They're typically managing a particular data set. So again, a data owner might be someone they control market data. They might control emissions data in the corporation. They're actually going to manage the asset entry, or entering and publishing the asset in the EDC system. So again, we've separated these two. In some situations, maybe it's the same person in smaller companies, but in larger companies, they would likely be different. Once you publish the asset, then it's now available to other participants that essentially satisfy the two sets of policies. So in order for a participant to be able to see those when they're essentially searching for data in the data space, they would have to, obviously fulfill the access requirements as well as the usage requirements. And I'll go a little bit further on publishing in a bit. Okay, so in terms of runtime policy enforcement, so we've talked a little bit about the essentially usage and how do I define it when I'm publishing data? How is essentially policies enforced at runtime? So for instance, this data that I'm sharing, it has to be stored in Europe. How would that work? So there's a couple, I think, important principles to cover here. One is essentially there is no single way to enforce policy. Okay, there's, for instance, there's lenient versus strict requirements. You might have a strict requirement like, this data has to be stored in Europe. There might be more lenient requirements, like, for instance, essentially you should only, or I should say soft requirements, you can only use this data for, emissions purposes, for analyzing CO2 emissions. You can't use it for marketing. That type of requirement, right? You want to be able to advertise or have policy, but there might not be an automated way to enforce that. So that's kind of one thing, is being able to handle that continuum. The second thing in terms of the diversity of this is really data has to traverse very diverse compute infrastructure. So for instance, if I'm sharing data and it has to be stored in Europe, well, the storage might be local on premise, or it might be in the cloud. Different participants, because we aren't enforcing one type of homogeneous infrastructure. The way the compute infrastructure that's involved in this is going to be quite diverse. So what we're going to need is essentially, there's no one way to do this. We're going to need a mechanism where you can plug in and account for this. Okay. And again, like I mentioned, some obligations might not be automated. So what this really requires, all of this is to say, what's really required is what I term a holistic coordination. So you need to, be able to, some obligations aren't automated. You need to be you need to have a way to advertise what the obligations are, essentially to a human, for instance. In terms of more automated, you might have to ensure that policy is enforced all the way down. So within your cloud environment, for instance, when the data is stored, you have to make sure it's stored in say, object storage that's in a European data center. So you need the coordination and the holistic view, essentially across all layers of your infrastructure. And the way we have this notion is what we call policy configuration, and I'll go through it in the next slide. Essentially, policy is configured and pushed down through the stack. So the real key to our policy, again, remembering, there isn't one way to do this. We couldn't come up with a kind of a completely closed solution that handles all cases. What we decided to do was create what we term a policy engine. And it essentially, what it boils down to, it's an extensible evaluation engine. So you can see here on what that essentially means is policy itself can be described in multiple different languages. So there's ODRL, there's IDS, which is a flavor of ODRL. There may be other policy languages. What we do, what the policy engine's responsible for is taking those as input, processing those into an internal policy model. And people familiar with, maybe building compilers and things, there's an abstract syntax tree is essentially created. So we have this internal model that's created from these different policy expression languages. And then what happens is the engine itself can runs over that and does evaluation. So it can make policy decisions. So an example of this, you can see here, if you have a data storage policy, what that does is that runs through the engine, and it would, if you're going to store the data, it's going to say pick a European. It'll use an API, for instance, to store S3 data in a European region. For instance, it could have, as part of that evaluation, it might deploy some Kubernetes policies, OPA. Okay, it could do other things. The important thing though is it's a pluggable mechanism. And again, like everything else in the connector, what we've done is we've created extension points so people can plug in policy modules into that. So you can have transformers or extensions that come in that work with, say, Kubernetes, work with different cloud storages, and those are contributed into the runtime. That's essentially how at a high level, how policies enforced. You can even plug in, for instance, to say you have a policy, only my partners can see data. In that case, you might have an extension that plugs into the policy engine that queries one of your backend systems, determine, okay, is this is this an active partner? So what we're providing is a hook and an engine to enable this. Okay, so I realize we're going to probably run short on time, and I want to leave some space for questions as well. What I'll do is I have a whole bunch of slides on the federated catalog service. So why don't I pause here? We could either go through this or I could field questions. So if Marcus or somebody, are there questions that are coming up that we should address, or should I continue?
Yeah, so some questions. So there are a lot of questions actually, but some of them are already answered. So I would say maybe add some words to the federated catalog service, and then that I don't know, let's have 8 minutes or something like that for question and answering. So okay, really great. Brief overview about the catalog service is indeed a good information.
Okay. So in terms of federated catalog services, the two key questions it really tries to answer is, how do I find data and how do I publish data? So aspects of these, right, is when I find data, is I only want to find data from trusted sources. I want to know what the usage policy is with that data, and I want to be able to query for data. Like I want to be able to, query across a data space. Similarly, when I publish data, right, I only want to be able to publish it to people I trust. I want to do it in a secure way, and I want to be able to protect my data with policies. Okay. Just briefly, I'll talk about kind of the problem and then the solution that we're trying to address with this. What I call fully and semi-centralized catalog architectures, these are where you really require a broker, where participants publish their data. So it might be, you publish it into a centralized broker or some type of semi-centralized broker, federated brokers. So in this case, each participant would publish their data, their assets, right? Not the actual data itself, but entries into one of these type of catalogs. Okay. The common issues with this is, one is around data visibility and sovereignty. So questions you have to ask is, in these type of architectures, for instance, is it acceptable for a third party to have access to an organization's data catalog? Third party being whoever is running the broker. Or is it acceptable for an organization to rely on a third party to advertise its data? Like, are you going to be sure that that broker is going to properly enforce your policy or your access restrictions? Similarly, like on a reliability and scalability side, and fully centralized or even semi-centralized systems, they raise a lot of scalability issues. So in terms of, when you're scaling up to thousands of participants, what happens if the central broker is down? How do you handle replication if you're in a semi-centralized system? So with the connector, we're trying to address this. And essentially the architecture we have is we're calling this federated catalog service. And we have two kind of components to this. One is the federated cache crawler and our federated catalog crawler and the federated catalog node. So essentially we have one piece that crawls other participants and another piece that provides, each participant provides their own basically catalog that's crawled by the others. So what that'll allow you to do is you can enable use cases like only allow my partners to access this data, only allow organizations, only organizations that are in Europe, for instance, can have access to the data. What that essentially means is this is essentially kind of the picture that we're aiming at, where each participant then houses their own node and their own crawler. And that gives a lot of scalability as well as essentially policy enforcement. I won't go into this in detail because I want to, leave things for questions, but, at a later date, we can also go into that. But it, essentially lets you even create more complex things where you have private partitions and essentially public partitions where you can basically proxy out, more public information, cache it and proxy it out to other clients, or you could have essentially, private partitions within the data space. But I just wanted to, I know that there's quite a bit to cover there, but just give you a little bit of an idea of what we're talking about with catalogs as well. So maybe I'll open it up here for questions. And Marcus, since I'm having
yeah, sounds good. So like I said, so there were a lot of questions and some already answered. Like Peter also wrote in the chat, so we will answer every question that was raised in the chat also after the event and publish the answers on the collateral GitHub repository. So maybe for this session here, Jim, I tried to copy out 3 different questions that we can answer right now. So one was, so how long does it take to adapt the connector to a particular use case? So of course, this is strongly related to the complexity of the case, but can you elaborate a little bit on the global ideas, so how to individualize the connector here?
Right. So the idea here is, again, like Marcus said, we have, you have a bunch of modules. It really depends on what you're trying to do. But, at a high level, the way we see this is, you have the core connector project. If you're familiar with Java projects, right, there's the modules get published to Maven or, Maven Central, right? It's similar if you're a node developer, it'd be kind of the equivalent of NPM. The idea then is you could, if you have, you want to build your own connector extension, you can just rely on those and build your own distribution. It really depends. What we're trying to do is offer is, a bunch of out of the box core functionality. So things like integration with Azure, integration with Amazon, and other key things like Postgres and key technologies. But depending on your use case, there might be some development involved, but it's really hard to kind of answer, in general. I mean, it could range to something very simple, like you want to plug in a policy module versus something more complex where you want to build out your whole infrastructure. But what we're trying to do is over time, provide more and more capabilities in the core.
Yeah, in the core, and also maybe then provide information where you can get other extensions, maybe that is not part of the core EDC open source project. So for example, you mentioned that there are a lot of technologies out there that can be used with its individual extensions. So of course, then selecting the modules that are required. That's the global idea. So, but then it depends on the use case.
And I think, we hope that they develop their own, they have their own repositories of EDC extensions, maybe for specific use cases that don't relate to the core functionality of the connector. Maybe it's for a particular vertical, for instance. They could have their own repositories and people could just plug those in as well.
Mm-hmm. So then there was the questions in the chat. So you mentioned some part of that, but so can you again talk a little bit about the negotiation phase? So basically, when does the negotiation takes place in each data or for each data transfer?
Sure. So that's a good point. So the way we did that as well as that's another asynchronous state machine. So I mentioned the transfer process part. The negotiation comes first. So there's a whole state machine and transition. It's basically a messages that are sent back and forth between the participant and the provider. And there's a bunch that we actually have kind of state diagrams and everything for how that works, but it essentially works in a similar way. And our goal is to eventually be able to even support manual approval or workflow. So policy could be something like you have access to the data once it's been approved by someone in the back office. We'd be able to support those scenarios. The idea though is that comes in when you do the data request. There's a negotiation first. You get a contract, and then once that's been approved, you actually get the data. You can request the data. And the key thing too is those are decoupled. So you could have done the contract negotiation ahead of time, then say 5 days later, you do the, you actually request the asset, or you're requesting the asset on an ongoing basis. You don't have to go through negotiation every time. It's basically you're just establishing a contract. Once the contract's been established, you can transfer data at will.
Mm-hmm. Okay, so yeah, let me check which other questions may be raised now. So there was another tackling REST API calls in combination with this asynchronous data transfer. So if there are more than one process required of the control planes to handle this REST API communication.
Okay, right. So how to do, essentially, I guess, how to get a REST communication? Like basically you want to proxy an API. I think we actually had one of the partners do that, and that's also we're working with the data plane framework on. So basically the short answer is there's a way to do it in there where you can actually do a kind of a synchronous request through for those type of use cases. Probably to go through the details of that would take long, but we could do that offline.
Mm-hmm. Sounds good. Yeah, and maybe also you can elaborate on that when we put the answers to questions in the collateral. So maybe then we can add some more information than we could right now.
Right. We might even be able to get Benjamin to help refer like how he actually did it.
Yeah, exactly. Yeah, perfect. So basically, since quite time is finished, thanks again, Jim, for giving us all the insights on the architecture. I think this was very helpful to understand how the EDC works and the concept will be implemented. And yeah, now we have a short coffee break.